Hi everyone, I am Juarez from Mexico and welcome to back the channel. Today we are going to build a complete industrial automation project titled Tank Level Control with Siemens L71200 and LabVIEW. We will program the automatic filling and emptying of tank from scratch, establishing a minimum and maximum level. And we will control it all using a custom SCADA interface. In this video, I'll show you how to set up the TIA Portal project, configure the network, establishing the data blocks for communication and declarable or variables. Let's get started. Uh, in TIA Portal, establishing the name. The project is nivel tanque. For me or for you is tank level. And my name is Juarez. The version is 16 in TIA Portal. And so create. And tank 1. Create. And the first, we open the TIA Portal and create a new project. And we added your device. In my case, it's an 6712200 PLC. Double click in IDT dispositive and so semantic and here in CPU in the case is CPU 10214 AC/DC RLAs and this option in my version is 4.0 in OK or create for you. Wait a few seconds, please. Before we write and code, we need to step up the communication parameters so our PLC can talk to the UPC server and LabVIEW later. And I double click in the PLC Ethernet port under Ethernet. In my case is this double. And I set the IP address to 192.168.0.1 in the software is this and save the project o guardar proyecto. Next, and this is crucial step is very important. We go to the CPU properties, navigate to protection and security, the connection mechanisms, and double click in PLC. Protection and security and mechanisms to connection. In this option, here we must check the box that says permit access with put and get communication. Without this third party software won't available to read of the write to PLC memory. Now let's organize your memory. In this case, instead of using scattered memory tags, we are creating a dedicated data block. If we add it a new block, and name is DB LabVIEW, in this case is open double db data in db lab view for communication in okay or aceptar save the project in, and organizing everything in a data block make the connection to a UPC server much cleaner and more professional. Let's declare or freeze a variable together. In this first round, under name, we type sensor crudo. Under data type, I will select int, which stands for integer. This variable will receive a simulator route analog input. In sensor crudo. In data type is int and save the project is very important. Now I will go ahead and declare the rest of the variable. We need forward set point and buttons. You can pause this video here and copy the list into your project. Now let's organize our memory instant or user SCADA memory tags. We are creating a dedicated data block. I will add a new block and name is db LabVIEW. Before adding variables, there is very important tricks. Right click in data block in the project to go to and properties and uncheck optimized block access. This is cancelled. In my case, no, nor uncheck and okay or accept that. We need standard access so the EOPC server can read the physical memory offset properly. Now let's declare it or variables exactly how we need them some or LabVIEW interface. First, under name, I'll type sensor crudo. For data type is select int, which stand for integer. Next, we type maximum and set data type to real. This will be our upper set point is this. Below that we type minimum also as real data type for our lower set point is this. And then we add our control buttons arranque as a ball for the start button and paro as a ball for the emergency stop is this to start or paro for emergency. Finally, we type level visual as a real data type for this variable that will send the scaled percentage back to our LabVIEW tank. Right now, you might notice that the offset column is completely empty. To generate this memory address, we must save and compile the project. And save this and click right, compile, ready. Click the compile button at the top and there it you can now see the specific offset generate for each variable. from 00 tom 2 and 12.0 we will need these exact numbers later for the UPC server. Now that our data block is ready, we need to declare our physical input, output, and memory tags in the PLC. In the project tree on the left, open the PLC tags folder and double click on show all tags. In this, before we start typing, here is a pro tip for better programming. Always add a description in the comment in this place column when you create a new variable. It takes 2 extra seconds, but it will save you a lot headshots when your project grows and you need to troubleshoot. Let's add our face tags together. Under name, it will type sensor de nivel. This. The data type is into to integer. And for the address, we will sync the physical analog input in for PLC, which is percent EW97. Finally, in the comment section, I will write physical analog input. What is this? Is for example, is a sensor physical, or if you force the signal, is to the signal that you force in LabVIEW or in the Bible. To save some time, I have prepared the complete list of all tags we need for this project. This includes our normalization and scaling tags, or PUBs or variable, physical output, and or memory bytes. I will leave the variable table on the screen right now. Please pause this video, create all these variables exactly as they appear with their specific data type and addresses, and a quick comment to H1. Okay, welcome back. Now that your tag table match mine, please don't forget the golden rule and automation. Go to the top left corner and click the Set Project button. We are now completely ready to write on ladder logic. Welcome back. Now we are inside our main block OB1, this double. Before we drag and drop an instruction, let's remind you of a golden rule in automation. I always document your code. You can see on my screen, I have given in my blog a clear tile, and the tile comment explain exactly what is done in both Spanish and English. Por ejemplo, este bloque contiene la lógica de programación en escalera ladder para el control automático de llenado y vaciado del tanque. Incluye el escalado de la señal analógica, el control de límites máximos y mínimos, set reset, enclavamiento de seguridad y la preparación de variables para la comunicación con la interfaz HMI en LabVIEW. This block contains the later logic programming for the automation filling and empty control of the tank. It includes analog signal, scaling, maximum and minimum, limit control, set reset, ferry, interlocks, and variable preparation for communication with the LabVIEW HMI interface. Um, You should also do this for every single segment. It separates the amateurs from the professionals and makes troubleshooting much easier. Now, let's go to a segment 1, signal scaling. Industrial season give a raw electrical value, no percentage. We need to translate that raw number into something our LabVIEW tank can understand. To do this, we use two mathematical blocks, norm norm x, and scale x. First, the norm x block takes a raw input in set the minimum is to 5530 in this minimum and the maximum to 2764A in this, which is the standard upper limit for Siemens analog input. The value pin receives in this receive the sensor crudo directly for DB LabVIEW. This block normalizes the raw signal into decimal value, which we output to a memory tag named nivel normalizado in this and out. And the memory is MD10. Next, we move the scale X block in this. We take the normalized value and scale it from 0.0 to 100.0 in minimum and maximus, representing a 0 to 100% fill level in the tank. The final output is sent train back on your DB LabVIEW into level visual variable in this nivel visual. And you like that our raw electrical signal is no perfect percent ready to be sent to our HMA screen. Moving on the segment 2, also always notice the script title and comment and the dot explain the logic. Here we build the brain of your automatic tank using as SR or set reset block. Our goal is simple. Automatically turn a pump on when the tank is empty and turn off when it is full. To achieve this, we use two comparator instruction. On the set input is this here. We place the last on the equal to block. If do you know, don't know where is this is in comparison in this only take and drop in any place. Is constantly compared on the current SCADA level, which is nivel visual here against our minimum set point for LabVIEW. In this, el set, in set is minimum. If the water level drop below the minimum threshold, the block send a signal to set or active or memory tag called on off bomba. In this case is this. On the reset input below it, we use a greater than or equal. In this case is this. This one compare our current nivel visual again list a maximum set point. Once the tank fill of the reaches this maximum limit is triggered to reset pin. This action turn the on-off bomba memory bytes back off, stopping the filling process. This simple but powerful set reset logic creates a perfect automatic and continuous cycle for our system. This is one um, of the most fundamental and important circuit and all PLC programming. Is the segment 3 is this. Ah, the start stop latch. Before we analyze the logic, notice a game or bilingual title and the title comment. Keeping your documentation consistent across every segment is a great habit for a professional engineer. Here we are using the arranque and paro tags we are previously created in our LabVIEW data blocks. The arranque or start button is a normally open contact. Is a normal open? It is a connect is serial with or paro in this contact close or stop button which act as normally closed contact. When we press start on your HMA screen, the signal passes through the close stop contact and energy the master. Koi called proceso el memory address M0.4. To keep the system running after release the start button, we place a normally open contact of the processor tag in the parallel with the start button. This create what we call a cell and circuit or enclavamiento. The system will now stay completely active until the operator presses the stop button, which breaks the circuit and turns everything off. This processor memory bit is essentially our master Safari condition, as we will see in the next segment. If this bit is off, nothing else in the system is allowed to run. Now we arrive at the segment 4, which control our physical output. Just like before, we have a bilingual title to clear. Comment display the logic. Here is where our start or stop latch from the previous segment goes to work. Notice that the very first instruction is in this row is normally open contact of our processor master bit. This means that if the system is not actively running, absolutely nothing in this segment can turn on. It is a crucial hardware safety measure. If processor is active, the signal is split into two branches. The top branch handles the filling process. Heat user and normally open contact of or on-off bomba byte, which come from reset block. When the tank needs water, this contact closes energy or physical pump output at the key 0.0, and this is simultaneously turning on the pump LED memory byte. And this is turning both. The bottom branch handles the empty process. It uses normally close contact of the exact same on-off bomba byte. This creates a mutually exclusive toggle. When the tank reaches its maximum level and the pump turns off, this normally close contact return to its resting state, allowing the signal to pass through. This automatically opens our physical discharge value and Q 0.1 and turn the value LED. So as long as the system is running, it will smoothly alternate between turning the pump on the filled tank and opening the valve to drain it. Finally, we reach segment 5. As always, our documentation. Wait, this documentation remains consist with a clear title and description. This segment is dedicated to provide a curated visual feedback for the operator. We want to turn on a stop LED on our LabVIEW interface, but only when system is available at rest. To guarantee this, we use a series of normally closed control. First, we check the pattern or stop signal from a data block. Then, and this is important part, we check the actual physical status on the bomba, in this case, output at Q 0.0 and or barbula output at Q 0.1 because these are normally close contact. The logic signal will only pass through on the stop button is active. And both the physical pump and bottle are completely shut off. If soldering conditions are true is energy, the LED pattern. Memory byte as M0.5. This is a great Safari practice. Is guaranteed that the HMA screen will only show the stopped status when the hardware has actually stopped, preventing any confusion. And with that, our PLC logic is 100% complete. Now, let's go to a NetToPLCL to bridge into TIA Portal and OPC server. Now that our TIA Portal logic is completed and running, we need to connect it to outside world. Since we are running a simulation and not a physical PLC, right now we need a bridge. That is where great to call it NetToPLCim. Com is before you open it. Pay attention to this very important detail. You must right click the NetToPLCim icon and select Run as Administrator. If you just double click it normally, the network port will be blocked by Windows and the communication will fail. Once the program is open with administrator privilege, we can proceed to configure it. The observation is don't run the TIA portal in simulator because the connection in TIA portal is broken. Okay. The first makes sure PLC simulator PLC is running and the CPU is running mode. Then click another PLC. Port is used. Before you can use to PLC, you have the program. Try to stop service. Yes. Is run the port. OK. Click in OK and add the the PLC. And this place you select the router. In my case is this is a Siemens PLC virtual Ethernet adapter. Click in OK. And this, if you don't run the TIA portal and simulate, don't show the AP, the PLC and TIA portal. Check. Not TSP and P reachable PLC detected. Please check it. PLC is running. In this moment is a pause to run the TIA portal, please. If you want to run the TIA portal, is in this case is here in start simulation. Click here. Wait a few seconds. And download the files in PLC. In nothing action, run module, final. When PLC is running, you establishing the connection online. And this moment is running the PLCM simulation. And let's go to a NetToPLCsim. Now, in this case is okay or accept. In this point, a network reachable PLC, network reachable PCL. The direction of the PCL is this, and okay. And rack is 0, and slope is 1, and okay. E is start server. Here status is running. It's okay. Um, Now I need to connect with OPC server. Click this here and show the icon. And this is the OPC server. Click right in this icon and configuration. In this moment, this is the configuration. If you know this table to variables, you need this. Do you need make this procediment? Is this, for example, new device, and the new device, for example, for me is PLC2. Next, device model is this is L71200. Next, device ID is 192.168.0.100. For example, is the direction. The network address is the same in device ID. Next, 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 next. The port number is 100.102. It's the same to a PLC. And next, 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 final. And did you know declare the variables is here? Click the variable. In my case, the declaration of the variable is this. For example, sensor crudo, double click, and this is the variable, and this is the address, and a description is here. If you know add this variable is applicant apply and the next tag. When do you finish this procediment, it's okay. Acceptar and running. I wait for you to declare all the variables. If you declare the variables in OPC servers, you select the PLC and quit client. If you select the PLC tank level PLC1, if you're the procediment okay, the variables all in quality is good. And the variable enable level visual or visual level is floatant because in TIA Portal the level is here. And so if your variable in quick client, it's okay, is good all. And now to proceed to open the LabVIEW to receive the variables and the values and manipulate the information and programming in LabVIEW all the structures to HTML to communicate to a TIA portal. Now that your OPC server is running, you you need to create a blank project. In this case, is this option, the first option. Finish. And to create, first is create a library. Click right in my computer, new, and EO server. And this option is OPC client and continue. And configure OPC client EO servers. Wait a few seconds because it's connected with a database with OPC server. And the option that you select is this National Instrument NEOPC servers version 5. And okay. In this moment, the library is here. The name is until library 2. And click in this library and clear right. And you select the create bound variable. Click here. Open the tree in here in my computer and until library 2 and OPC 1 and PLC tank level and PLC 1 in this moment all variable is here. You select this variable and this and this and this all the variables and add in this moment add variable in OK. And in this moment you explain the tree and this is all the variables. You open here in my computer, clear right a new BI and you take this and this and this and this and this and this and this variable and drop and put in a block diagram 1 2. In this moment all the variable is ready to use in LabVIEW. Ready. With our PLC communication ready, it's time to build our HML in LabVIEW. As you can see on my front panel, this does not look like a standard boarding software. Is look like a real professional industrial SCADA dashboard. To achieve this realistic look is simple. Design a dark brushed metal background image drag it directly into my left front panel and uses the reorder tool to send it to the back. On the top of this background is placed on control or indicator. On the right we have a tank director in display is 0 to 100%. In this place is this in properties. You can change scale the 0 or 100. In the middle, you place a vertical light or use sensor crudo. In this case, is this. And the minimum is 5530 and maximum is 27648. Notice that the scale exactly match on the Siemens analog input from 5530 and the both to 27648 and the top. On the left, I added two numeric displays for maximum and minimum start point and two large custom LED. It represents the physical status of your pump and the Bible. In this case, is this and this is the LED pump and the LED valve. Finally, at the both, we have our start or stop buttons or control the system latch. Is in ranker or start or paro or stop or out and salir. Now let's press Ctrl A to look the block diagram. In this case is this and see how everything is connected because we did the hard work in TIA Portal. Our LabVIEW code is incredibly clean and simple. There is no complex logic here, only data reading and rating. First, everything is placed inside a standard while loop. This keeps our HMI running continually. Inside the loop, and added a wait function set to 100 millimeter. Is this milliseconds? This is a crucial best practice to optimize the computer CPU while still maintaining real-time communication. To connect the graphic to our PLC is simple, degraded or enable publisher chart variables directly from a project library into the log. Let's look at the data flow. For the data going to the PLC, we have our console. I wear the sensor crudo, slide the arranque start button, and the paro stop button directly in their respective network variables. This means when we move the light and click a button, LabVIEW write the command instantly in L71200 memory. For the data coming from the PLC, we have our indication where the LED bomba and LED válvula máximo, mínimo, and nivel visual variable directly into our front panel graphic. LabVIEW constantly read this value from the Siemens data block and update the screen. Finally, a separate stop button is wired directly to loop condition to Safari terminate the application when we are done. Okay, now okay, now I need to make a test to a functionation the control. In TIA Portal is running the PLC in simulated state. And did you want to see the change in the diagram? Click here and it's running. When you change in crudo in this variable, you can see the value in the norm X is up and the level is changed more. For example, in this place, in level of tank is up. In the maximum, for example, is 80. In this segment 2, the value is changed. In this 80, for example, minimum 20, and the console is running. Now for okay, if you can see the values, can you see the values to in the OPC server? If you can change this value, this variable is changed too. And this, everything is okay, and the value is changed in visual level. In level level is to change when you when you change the sensor crew, the change is to in the level of the tank.